Okay, so for today's lesson, I'll be going through the main highlights of the Chatelain principle. So I hope that you have already copied down the notes. Okay, so before this, we were discussing the effect of the concentration, whereby we can increase or reduce either on the reactor side or the product side. Okay, so for this, what we are talking about is changes in pressure, and the effect is only on gaseous particles. Okay, it doesn't affect the concentration of the aqueous ions. It only affects the gas particles. Okay, so we can see for ourselves, right? When we mention or we use the term total pressure, we are referring to the actions on the volume of the vessel. So if I shrink or if I expand the volume of the vessel, it will affect the concentration of every gas particles in the system. Okay, so when I reduce the volume in this Haber process, I will see the concentration of nitrogen, ammonia, and hydrogen all increase simultaneously. Okay, so that is the effect of this. Reducing volume, all will shoot up at this instance. Okay, so when you read a graph and you observe them shooting up simultaneously at that particular instance, that must be due to changes in volume of the vessel, nothing else. Okay, so if it's just one particular increase, then that is through introduction of that particular substance only. No effect on the volume of the vessel. Okay, so when you read the graph, you must know what is going on. Okay, so other than the position of equilibrium, we also need to consider the effect of rates. Okay, so we emphasize this relationship. Total pressure in a vessel is proportional to the total number of gas particles in that constant volume. Okay, we always associate total pressure to the number of moles of gas in a particular volume. Okay, so the POE can change if there is a difference in the number of particles on the reactant side and the product side. But let's say, okay, in the case of when there are equal number of gas particles. So some of you, right, when you submit your tutorial, you are very careless because you did not double check on the state symbols. When the equation is given to you, especially when there's state symbol, and we are discussing the effect of volume change, okay, we need to see that these are two gaseous particles on the reactant side. Again, only two gaseous particles on the product side, ignoring the solid state or even the aqueous state. Okay, because solid and aqueous are not affected by pressure. Okay, so in this case, right, what do you think will be the effect of the POE? How will it affect the rates? Okay, so obviously, when I change the volume, the concentration of the gaseous particles will be affected simultaneously. All will increase or all will decrease at the same time, depending on how I change the volume. Okay, but then because on either side, there's no way I can reduce the number of gas particles. Okay, so the POE will be unaffected. Okay, so Johnny, what do you think? Will the rate be affected? Okay, we know that POE will not be affected, but will rate be affected? Why? There's a change in volume. Yeah, so in this case, right, POE, we apply the Chatelain principle to partially offset the disturbance. For rate of reaction, we refer to collision theory. All right, so what does collision theory tell us? What could have affected the rate? What can affect rate? Do you still remember your collision theory? What can affect rate? Huh? Okay, Anya, you just arrived back. So can you recall what affects rate reaction? Now that we have done the Chatelain principle, right? Then can you recall what we have learned from rates? Concentration, yeah. So concentration can affect the collision frequency, which also affects the effective collision frequency. Okay, what else? What else can affect rates? Kids, what do you think? temperature. Yeah, so temperature can increase or change the average kinetic energy of the particles. And of course, when the average kinetic energy increases, there can be a higher proportion of particles having energy more than or equal to activation energy. So that will, of course, be related to the number of effective collision, right? Frequency. Okay, then what else? What else can affect rate of reaction? Other than concentration, other than temperature. What else? You know the thing. Huh? Pressure and catalyst. Okay, pressure is the same as concentration. Yeah, so we use the term pressure when we're talking about gaseous particles. But pressure of a gas is proportional to its concentration in that reaction vessel. Yeah, okay, so they are the same effect, right? So we use the catalyst. If we use the catalyst, it can lower the activation energy, which could help us increase the effective collision frequency as well. Okay, so you notice that when we talk about rates, we refer to collision theory. Okay, when we talk about U, extent of reaction, POE, we consider the Chatelier principle. Okay, they are isolated. Okay, do not mix them up. Okay, collision theory is about rates, LCP is about extent of reaction, POE. They are not together. They are independent. Okay, so you must know what we are talking about. Huh? Am I asking about rates? Am I asking about POE? Okay, we apply different theory. Okay, so this one you must appreciate. There's no change in POE because there's no difference in the number of gaseous particles, but the rate definitely change because the concentration of your gas particles changes. Okay, so this is what you should have copied down also. Any issue from here? Yeah, right. So if I increase the total pressure, the concentration of the gas particles increase. It will shoot up. Therefore, the equilibrium resists the change by reducing the number of gas particles. The gaseous system cannot change the volume. Huh? It can only change the reactants, the reaction. Okay, so the reaction can only respond by changing its number of particles, gas particles. Okay, so similar idea, if you reduce the pressure, it will have to up the gas particles in order to resist that change. Okay, right? So this is what you should recognize. So from here, right, okay, why is it that changes in POE due to the changes in pressure will not change your Kc value? Okay, so let's look at this particular example over here. Okay, the Kc expression looks something like this, right? So when I increase the total pressure of the system or reduce the volume of the reaction vessel, I should see an immediate increase, okay, in both the numerator and the denominator. Okay, then this is the disturbance. Therefore, it will take some time to respond to the change. Okay, so we all agree that it will shift to the right, shift to the product side in order to reduce the total number of gas particles. So as it changes, the new equilibrium will have more of the N2O4. Agree? Because it shifted to the right hand side, right? Product side. Okay, then at the same time, the N2O will be reduced, right? In order to form more of the N2O4. So this is the change. But there's one thing I want you to appreciate. Okay, the change is only partially offset. Okay, at that instance, both will increase. When the new equilibrium is attained, please appreciate that this is still higher than before. Okay, higher than this one. Okay, it's just that it's partially offset. Okay, this one is higher because we favor the side with the less gaseous particles. So you can see for ourselves, because of this is power 1, this is power 2, both are increased, but to a different extent. The fraction is still the same as before. Yeah, both increases, right? This one smaller extent, but it's power 2. This one is power 1. So they will cancel out each other and maintain the value of Kc. This is how it works. Okay, so that's why you can see for yourself that Kc value is not. Okay, so this is the effect of temperature. I'm sure that you have already copied this, right? Okay, so we emphasize this sum of the excess energy. Okay, why do we emphasize this? Because we do not remove all the energy added to the system. We only remove partially. Okay, that is the Chatelet principle. Okay, we do not remove all of the excess energy. We only remove part of the excess energy. Okay, so same thing here. We will release some heat energy to partially offset the drop in. Okay, so all this you should recognize that Kc will change when temperature changes, right? Okay, so these are things that we have copied already. So let's look at the exothermic reaction. For exothermic reaction, it means that heat energy is given out as a product. Okay, so I can put the heat concentration here to help me think along the LCP principle. Okay, so you can see that when there is a sudden increase in temperature, I'm putting in heat. So the concentration of heat will increase, right? Then when the heat energy concentration increases, how will the POE respond? It will shift to the left, right? Because there's a surplus of heat energy here, it will shift backwards in order to remove part of the heat energy supply. Okay, so you can see for yourself that your product, okay, will decrease while the denominator, the reactant, will increase. So because of this, both will make your Kc value larger. They will not be able to offset each other in terms of the numerator and denominator. Can see? So that's why Kc will change with temperature. All right, and how it changes depends on whether it's exothermic or endothermic. So you must be very careful. When you talk about the effect of temperature, you need to look out for whether it releases heat energy or absorbs heat. Okay, when you talk about effect of pressure, then you need to compare the gas particles, the number of gas particles on the both sides. Okay, so you need to know what to look out for when there are different disturbances to consider. Okay, all right, is it okay? Fair enough. So you can see for yourself, right? Okay, so the rest I will not go through that. Okay, so in this case, of course, reactions with zero enthalpy, which is very rare. Okay, then there will be no effect of temperature. The temperature will have no effect on the POE. Okay, but of course, you should recognize that the rate will be, because temperature will affect the average K. Okay, so no effect on POE, but doesn't mean that there's no effect on rate. Okay, remember that. Right, so this is what you should have copied also. Okay. All right, so let's look at the effect of catalyst on the equilibrium. Okay, so way before, right, before you start this LCP series, we are talking about the effect of catalyst without and with catalyst. So can someone tell me what's the relationship between these two? What's the relationship? Okay, Anshan, what do you think? What's the relationship between these two? Do you see any relationship or any effect? Huh? Final concentration. Final concentration or concentration at equilibrium? Yeah, it's more accurate to talk about it as a concentration at equilibrium, contributions equilibrium. Yeah, so what about the concentration that is dynamic equilibrium? What about the concentration? What about the concentration? Yeah, it's the same. Okay, so we can see that the blue horizontal line is trying to tell you that With or without catalyst, when it reaches equilibrium, the concentration of the reactant and product is exactly the same. That's provided the starting concentration for both systems is the same now. Right? We're assuming that. Okay, so you can see that catalyst has no effect on the POE. It doesn't change the position of equilibrium. It has no effect on the percentage yield. Okay, now what is being affected? Okay, Donnie, can you tell us what is being affected in this graph? Yeah, so you can see that T1 is definitely larger than T2. Yeah, okay, so T1 is definitely larger than T2. Okay, so that is the effect of this. So if you have a initial starting point reactant and you add in a catalyst, it should take a shorter time to attain equilibrium compared to the same reaction without catalyst. Okay, right? So that's the two relationship. Okay, so let's look at this Born-Haber process. This is on page 23 of the lecture notes. Okay, so why only ammonia is liquefied on the cooling coil? This is the cooling coil. Okay, so basically this is the reaction mixture, which we know that is a reversible reaction. It's never complete. So this mixture will be passed through this cooling coil, whereby only ammonia is collected, while the nitrogen and hydrogen will be connected back to the reaction system again and for further reactions. Okay, so can you tell me or can you answer this question? Okay, to your elbow partner, right? Try to explain to each other why only ammonia is liquefied and how does liquefaction of ammonia proceed? There must be a reason why we do this, right? So why does it proceed? What does it do? Can you tell your elbow partner what's going on? What do you think? Why only ammonia? Why not hydrogen? Not hydrogen being liquefied? Why not? What does it do? What do you do? Not very well. Okay, who can answer the first question? Doing what is it? NH3, yes. Okay, NH3 has a different boiling point. But is that sufficient to answer why only ammonia is liquefied in the cooling coil? just say that ammonia has a different boiling point. Okay, it's good that you recognize that it's a physical property that we are looking at. All right. So can we make the answer better? Why ammonia has a different boiling point, or rather, is it higher or lower compared to hydrogen and oxygen? Higher or lower? Lower. Ammonia has a lower boiling point. If it's a lower boiling point, is more volatile or less volatile? Lower boiling point, more volatile or less volatile? Okay, lower boiling point, easier to evaporate or more difficult to evaporate? Easier to evaporate, right? Lower boiling point. So if it's easier to evaporate, then is it easy for us to liquefy it? If it's easier to evaporate, is it easy for us to condense it? Confused. Huh? If the boiling point is lower, it's more volatile. So, is it easier or more difficult to condense? What is it? So should be more or less? More. Boiling point. Boiling point of ammonia should be more or less than hydrogen. More or less. If only ammonia is liquefied at the boiling point, right? So what should be the boiling point compared to hydrogen? Higher. So why? More volatile. If it's more volatile, then is it easy for us to liquefy it? Liquefy means you condense it back to liquid. Okay, boiling point is related to the iron mass strength, right? Correct? Yeah. So if only ammonia is liquefied, while nitrogen and hydrogen is gaseous, what does it mean? Which one has stronger intermolecular force? Ammonia or nitrogen? When you force the gaseous particles closer towards each other, they can only become liquid if there's significant intermolecular attraction, right? If they experience negligible intermolecular force, they will exist in gaseous state. No attraction, so gaseous. All right, they go around individually, no effect on each other. But they can only be liquefied if they experience attractive force with each other. They are bound to each other. Yeah, then when it becomes solid, of course, the attractive force will be the strongest. So can you see why ammonia is the only one that is liquefied? Is it confusing? No? So what do you think? Which one? Boiling point higher or lower? Should be higher or lower? Anya, what do you think? Huh? Lower. Why lower? If it's higher, if boiling point is higher, it's easier to evaporate. If the boiling point is higher, it's easier to evaporate. Is that correct? Yeah. Yeah. So if the temperature here is say minus 10 degrees, okay, if the cooling coil has a minus 10 degrees Celsius temperature, then the boiling point of ammonia, okay, hydrogen and hydrogen. Okay, so what does boiling point mean? They want to do a search. What's the boiling point of ammonia, hydrogen and hydrogen? Do a search. Boiling point of ammonia is negative 23 degrees Celsius. 30. Okay. How about it? Next one, hydrogen. Hydrogen. Negative 2.2. What is this? Negative 196. So what should be the temperature of my cooling coil such that only this is liquefied? What should be my temperature of the cooling coil such that only this is liquefied? Negative 40. Yeah. If the cooling coil is negative 40 degrees Celsius, what does it mean? At this temperature, what is the physical state of your ammonia? Does it boil? This one is lower in energy compared to this one. Hello, this is negative sign. Hello, this negative sign. Okay, this one is of a lower temperature than this one. This one even much lower, No? This one is the lower side because hydrogen is the smallest mass. Okay, so if the cooling compartment is of this temperature, this will be liquid state because this is below its boiling point. This temperature is below its boiling point. So this will be liquid. While this temperature are above the boiling point of hydrogen and nitrogen respectively. So this will remain gaseous. You can see? Yeah. A substance can only boil if the temperature of the surrounding is at its boiling point or higher than its boiling point. Agree? Agree or not? A substance can only boil, right? If the temperature is higher than its boiling point. This one is lower. So only this can liquefy. While these two will remain as gaseous. So what does it mean? What does it mean? This has the strongest IMF, right? So what is the IMF between ammonia? What's the IMF between ammonia? Chemical bonding. What's the IMF between ammonia? Huh? What is it? Huh? ID only? Now this one is a 17 MR. 17, this one is 2, this one is 28. So if it's ID, right, by right, nitrogen should have the highest ID, strongest. But then the boiling point is not consistent. So what should be the IMF between ammonia molecules? PD, hydrogen bonding. Yeah. Okay. So for IMF, right, always look out for hydrogen bonding first. What's the criteria for hydrogen bonding? What's the criteria for hydrogen bonding? There must be a lone pair. Any lone pair? There are many atoms with lone pair. So all atoms with lone pairs can undergo hydrogen bonding? No. Okay. There are a lot of central atoms with lone pairs as well. So does it mean that all central atoms with lone pair can undergo hydrogen bonding? Huh? Do you still remember? You must remember, this one is chemical bonding. Where should the lone pair be? NON. NOS, lone pair, NOS can take part in hydrogen bonding. But before the lone pair, right, you should consider the presence of what? For hydrogen bonding to take place, you should consider the presence of hydrogen, photonic hydrogen. Photonic hydrogen. And is there a photonic hydrogen here? Yes, there's a hydrogen directly bonded to your nitrogen. Okay, so photonic H, okay, is H directly bonded to N, O, or N. Okay, these are your photonic H. So this must be present first. Then you consider the lone pair on NOS. Okay, so obviously ammonia satisfies this criteria. So even though it has a comparable mass or lower mass than your nitrogen, it has the strongest ion mass because of H bonding, which makes the boiling point the highest, hence the only one that liquefies. Okay, while hydrogen and nitrogen can go back to the reaction system and react further. Okay, so how would the liquefaction of ammonia help in the U? Can you see how? In this reaction system, all of them are in gaseous state. So when ammonia is converted to liquid, what are you doing? When ammonia here goes through the cooling coil, and the whole thing goes through the cooling coil, and only ammonia liquid is collected. How does it help you increase the U? What is it equivalent to? What is it equivalent to? Eva, what do you think? What is it equivalent to? When I say liquefaction of ammonia, what am I doing to the system? You are increasing the pressure. Increasing the pressure. How would liquefaction increase the pressure? Decreasing the volume. Cooling system, right? That means the temperature is reduced. Cooling system, cooling means what? You remove heat, right? Then why would that cause an increase in pressure? Doesn't make sense, right? Does it make sense? Yeah. So why would the liquefaction of ammonia pushes the equilibrium forward? How does it work? It's an exothermic reaction. So when you cool it, it will try to release heat to partially offset. Okay, yeah, okay, that is true. So when you try to cool it down, it can push the equilibrium forward. But how would liquefaction look then? You're not answering the question. I'm not discussing the effect of temperature. I'm specifically asking you to consider why would liquefaction increase you? You get my question? Yeah, we are not just generally discussing the effect of temperature. In your H1 assessment, you need to know to pick up important points from paragraph of words or even from a diagram. Yeah, how would this work? Now, when you convert gaseous to liquid, what will happen to the concentration of the gaseous ammonia? In this reaction system, they all react in the gaseous state. So when I convert this gaseous to liquid state, what am I doing? What am I doing? I'm removing ammonia from the reaction system. Okay, that is essentially decreasing the concentration of ammonia. Yeah, so when I liquefy my ammonia, I'm essentially decreasing the concentration of gaseous ammonia. Hence, the equilibrium or the POE will have to shift forward to partially offset that change. Okay, so number one, recognize that this is a gaseous reaction. Gaseous reaction. Okay, so the physical change from gaseous ammonia to liquid ammonia will affect the concentration of the gaseous ammonia. Therefore, POE will shift to try to partially offset. Okay, so that's how it works. Is it okay? Yeah. Yeah, so let's look at the exercise 1.7. Exercise 7. Okay, so in this case, we are talking about the effects of concentration, temperature, pressure, as well as catalysis. Okay, so for part 1, we are talking about the concentration of reactant A and concentration of product C. Okay, so for this disturbance, we are only considering the rate at that instance. Okay, so forward rate definitely will increase or decrease. When you increase the concentration of either of the reactant, definitely the forward rate will increase according to the collision theory, right? So the position of equilibrium, of course, will be shifting to the right according to LCP, right? Okay, then the effect on Kc is no effect because temperature has changed. Yeah. Okay, so I hope by now you recognize that Kc will only change when temperature change, nothing else. Okay, so if we increase the concentration of the product, then of course the backward rate will increase at that instance. Okay, then it will shift on the opposite direction, shift to the left, and of course same thing, no effect on this. Okay, so when you talk about the effect of temperature, according to collision theory, it should increase. Okay, but whether it should right or left, how do you tell whether the temperature will shift right or left? Now, when I say overall rates, what do I mean by this? Why is it that for the first two, I talk about forward rates, backward rates, but for here, I talk about overall rates? What do I mean by this? Is there a difference? Is there a difference when we talk about forward, backward rates versus overall rates? Is there a difference? Huh? Is there a difference? Jamie, what do you think? There's a difference. So what's the difference? What do I mean by overall rates? Both rate forward and rate backward will increase. Yes, good. Right? So overall rate means both the forward and the backward rate. Because both the reactant and the product molecules have gained in kinetic. Okay, so the effective collision in both directions. Right? Okay, so in this case, whether it shifts right or left depends on the enthalpy change. Okay, whether it shifts right or left depends on the enthalpy change. So since it is exothermic, it means that heat energy is released. Okay, as a product. Okay, so you must recognize that in order for you to tell whether it will shift right or left. Okay, got it? Right. So in this case, right, since it shifted left, this means that there's decrease of product, increase of reactant. Hence, Kc will decrease. Okay, yeah. Right, so in this case, right, if I drop in temperature, then of course the overall rate will decrease. Okay, due to the decrease in average Ke. Okay, and of course it will shift right. just now shift left, right? And now it's opposite direction, of course. Okay, and this one will increase because it favors the product, reduce the reactant. So Kc will increase. Okay, so over here, changes at this point of time. So when you increase the pressure, all concentration will decrease. When you decrease the pressure, all concentration will decrease at that distance. Okay, and when I talk about concentration here, I'm only referring to gaseous particles. Okay, so when I talk about concentration here, I'm only referring to gaseous particles. Okay, so if there's an increase in pressure, there's increase in concentration, therefore increase in rate. And it's an overall rate now because all increases. So both backward and forward will increase. Then of course, by comparing the number of gas particles on both sides, we recognize that in shift right. Okay, because that is where there's lesser gaseous particles. Right, shift right, because that is where there's lesser gaseous particles. Okay, not an enthalpy change. And this one no change because no change in concentration. Now, of course, if your concentration drop, then the rate will decrease according to your collision theory. Okay, and of course, it will favor the side with more gas particles. Okay, in order to increase the concentration of the gas particles. So again, no change because no change in temperature. Right? So with this, right, we emphasize that changes in pressure affects only the gaseous particles. Okay, concentration of aqueous ions are not affected by change in volume of the vessel. Okay, so when will the concentration of all ions be affected? When? If I change the volume of the vessel, it doesn't affect the concentration of the aqueous ions, right? So then when will it change? What kind of disturbance can I do to the system in order to change the concentration of all aqueous ions? What do you think? The volume of the solution is different from the volume of the vessel because it's a liquid state. Liquid doesn't occupy the total volume of the vessel. Yeah, the total volume is the liquid domain. So how do you propose that I can affect the concentration of all the aqueous ions in this liquid state? How? Changing volume of the vessel doesn't work. Then what can we do to cause this to happen? What can we do? What contributes to the volume of the aqueous solution? How can I change the volume of the aqueous solution? Add water, yes, good job. Add water. Okay, by adding water, because aqueous solution, water is a solvent here. Okay, so if you add water, it will increase the total volume. Then all the concentration of the aqueous ions will drop at the same time because total volume increases. If I evaporate the water away, then it will result in a higher concentration of the aqueous ion because there's lesser total volume for the aqueous solution. Yeah. Okay. So essentially they are the same. It's just that the disturbance is different. Okay. Volume of the vessel affects only the concentration of gaseous particles, while addition of the solvent or removal of the solvent affects the concentration of the aqueous ions. Okay. Right, so the last part, of course, is the addition of catalyst. Overall rate will increase, but no change in POE, no change in the Kc value. Okay, so this is the last. All right. Okay, so I will look at the tutorial now. Okay, most of you will give the correct answer to question 1B, self-attempt. Okay, all of you know that the first two statements are false. Okay, And I would like you to elaborate more. So all of you recognize that Kc is not a measure of rate. Okay, so larger Kc simply implies that POE is more to the right hand side, or it favors the product side. Okay, but it doesn't tell you how fast this is. Okay, then of course catalyst is, it will never affect the Kc value. Is it too small? Okay. Can I think it's the C statement, which this one is more challenging. Okay, some of you say false, some of you it should be a true statement. And I need you to recognize that it is partially offset. Okay, so decrease in volume causes the concentration of all substances. In this case, all gaseous substance to increase, and the POE will shift to partially offset this change. Okay, so the new equilibrium concentration, right, definitely will be higher. Okay, all of them will be higher. Okay, because some of you thought that not all will be higher. Okay, in fact, all will be higher. Okay, what do I mean by this? Who disagree that all will be higher, or only part of it will be higher? All of the equilibrium concentration will be higher. Why so? So if you look at this example again, now we have 3 hydrogen plus nitrogen to form ammonia. Okay, so when all of them shoot up due to the decrease in volume, okay, it will shift to the right hand side, right? So as to reduce the number of gaseous particles. Okay, so as the hydrogen and nitrogen is reacted away, it will drop. It will drop. Well, this is the only one that increases. So can you see that this part is still higher than the initial equilibrium pressure? This is definitely higher because the POE shifted to the ammonia side. This is still higher than the initial. Okay. Yeah. So when a new POE is attained, the equilibrium concentration is still higher than before, than the initial equilibrium pressure, definitely, when it shifted. Okay, so this statement is true. Okay. I move on. I mean, if you cannot understand, I can explain again. Doesn't matter. Can? Can? Okay, let's look at this. Okay, most of you are able to tell whether there should be a decrease in total pressure or increase in total pressure. Okay, so some of you are very careless. You did not check out for the number of gas particles. Okay, so you should be aware that only the gaseous particles will be affected. So for second example, this is 3. This is also 3. So therefore, there's no change. Either you shift right or shift left. Hence, changes in pressure will have no effect, okay, on the POE. Okay, so I need you to recognize what is the significance of the total pressure. It refers to the everything will increase. That's the meaning of total. It's not one particular pressure, it's everything. All the pressure of the gas particles will increase at the same time, or all of them will drop at the same time. So that's the meaning of total pressure. Okay, it's not just one substance. Then question 4, I think is pretty straightforward. Most of you can get the answer, right? Okay, then this one is just basically lifted off from your lecture notes, so should be quite straightforward. Okay, so B part 1, okay, these are some of the answers from your peers. Okay, so some of you are very organized in your explanation. Okay, good job, very elaborate. Now learn to elaborate your answer. Okay, So what we are talking about here is, what is so good about this answer is, number one, she stated very clearly that this is the disturbance. Okay, this is the disturbance. And in her explanation, she incorporated the essence of the Chatelier principle. Okay, trying to reduce the chlorine, right? Therefore, PCl5 will increase in concentration. Okay, then she went on to elaborate that Kc no change, because no change in temperature. Because sometimes, right, the question will require you to explain. Yeah, so do not just say Kc unchanged. Justify why you know that there's no change. Okay, how could we make this answer better? Is the Le Chatelier principle accurate here? Is the chemistry principle LCP accurate here? Now, when you say reducing the chlorine, what must you emphasize? What must you emphasize? When you say reducing the chlorine here, right? Do you refer to 100% removal or partial removal? 100% removal, complete removal, or partial removal? You should emphasize is counteract by partially reducing. Okay, or reducing some of the chlorine added. Yeah, you have to emphasize the partial part. It's partially offset. Okay, so over here, okay, I like the answer also. So you can see that there's this disturbance introduced, then counteracts by releasing more heat. Okay, you will shift to the left. This is the exothermic reaction. Okay, then she made reference to the Kc expression and hence explain why Kc will decrease. Increase or decrease? Kc value will increase or decrease? Temperature decrease, counteract by reducing more heat, will shift to the left. Okay, so the Kc will decrease. Yeah. Okay, so you can see that the answer is very straight to the point. Yeah, straight away I can see why Kc value will decrease by making reference to this. Okay, so this is the effect of the volume of the vessel. Okay, good job in highlighting that you are trying to increase the concentration of the gaseous molecules. Now, she's not making reference to either the reactant or the product. She's referring to the concentration of all the gaseous particles. This is exactly what is happening here, the effect of pressure. Okay, to increase the concentration of gaseous molecules. This is essentially what we are doing. Okay, and you can see that she justified by comparing the number of gas on the reactant side and the product side. Yeah. All right. Okay. I think we have come to the end of the lesson. Then the next lesson I see where I will complete this tutorial. Then I will administer the test. Okay. If there's time, then I'll start acid-base equilibrium. Okay. Right. That's all for today.